Hi, I'm Kathleen Wittmann from Rockwell Automation. Rockwell is a global leader in industrial automation and digital transformation. We bring the connected enterprise to life by converging plant-level and enterprise networks and securely connecting people, processes, and technologies. I recently moved into a team lead position, but prior to that, I spent over 10 years verifying ASIC and FPGA designs and managing numerous FPGA developments. I'm here today to talk about the power of UVM and provide insight into how and why to harness that power. Following a recent ASIC project retrospective, I was asked to explore methods for improving simulation efficiency at my organization. In exploring the methods, it helped to first understand the simulation flow, which is shown in this diagram. The source code for the design and the test bench is compiled into a work library. Then that work library is elaborated. Finally, the elaborated snapshot is simulated. Simulation efficiency can be achieved if one or more of the steps can be eliminated or shortened. This slide defines such methods. Incremental compilation eliminates or reduces compile time by only recompiling modified files. The use of elaboration snapshots eliminate both compile and elaborate by using a previously elaborated snapshot and jumping straight to simulation. Think of this in the context of a regression. The design and test bench are elaborated for the first test of the regression, and all other tests use the output of that elaboration. Both incremental compilation and elaboration snapshots allow reuse of previously processed data so that more time can be spent in value-add simulation. Simulation snapshots allow even more reuse. A simulation can be snapshotted at a particular time, such as after a lengthy initialization sequence. Rather than repeat this initialization sequence in every simulation, subsequent tests can pick up where the snapshot left off and introduce new stimulus. This approach saves valuable compute time for new and unique stimulus. There are two key requirements for incremental compilation and elaboration snapshots. First, the same work library must be used across tests. As you can see in the figure, the output of compile goes into the work library. Then the work library is an input to the elaborate step, the output of which also goes in the work library. Finally, the simulate step draws upon the work library. To have the same input for every simulation, the work library must be the same. Additionally, the same static test bench must be used across tests. Without the same static test bench, compile and elaboration must occur again. I found that my organization violated both of these requirements. We were creating a new work library for every test in our regression, and the prevalent use of macros and conditional compiler directives meant that our test bench was not static across tests. This code snippet demonstrates the use of these conditional compiler directives. In the test case that define the USB macro, the UVM environment will include the USB agent. In test cases that do not define the USB VIP macro, the UVM environment will not include the agent at all. This is a different static environment between the two cases, and it means that the files have to be recompiled and re-elaborated whenever different macros are used. This was a key realization about our test bench. While we were using elements of UVM in our test bench, we had not fully migrated away from using Verilog compiler directives to statically configure our test bench. We had not yet adopted the full power of UVM to dynamically configure our test bench. This lack of dynamic configuration was causing us to miss all three simulation efficiencies we wanted to adopt. This annotated simulation flow shows the impact of the static test bench configuration and separate work library. In the benchmark I performed, I found that these tests were taking on average 0.8 minutes to compile and 7.6 minutes to elaborate. By not leveraging the dynamic configuration power of UVM, we weren't able to optimize this flow. Had we been able to compile and elaborate once and then use the elaboration snapshot to jump straight to simulation, we could have saved nearly 12 days of processing time over our 2000 test regression. I showed you a couple slides ago the statically configured UVM environment we had. The rewritten environment on the right demonstrates how it can take advantage of the dynamic configuration power of UVM. Here, the USB agent is always a member of the environment, but whether it is built depends on how the environment has been configured. You'll notice that the has agent USB variable in the environment configuration object is checked to determine whether or not to create the agent. Here you see the declaration of that has agent USB variable in the environment configuration object. Also shown here is the test base class. The UVM test configures the UVM environment through the use of the variables in the environment configuration object. You can see here that the configure.env function is setting that has agent USB variable to 1. This slide shows how the object-oriented programming's polymorphism concept adds power to UVM. So I just showed the test base class. Tests that inherit from that test base class have two options. Shown in the top right, a test that inherits from the test base class can use the base class's function to do a default configuration. Here, test with USB inherited from .testbase and did not define an overriding configure.env function. When this inherited test then calls super.build, it executes the configure.env function that is defined in the .base test. This is because no overriding function has been written. Shown in the bottom right, a test that inherits from the test base class can declare its own overriding function. This overriding function follows the same prototype as the function in the base class, the same name, inputs, and outputs. Because virtual methods are inheritable and overridable, there's only one implementation of a virtual method per class hierarchy, and it is always the one in the last derived class. When this inherited test then calls super.build, it executes its own overriding function. Instead of the function in the base class, the function in the derived test without USB class is executed. It sets has agent USB to 0, resulting in the USB agent not being created. The key to this polymorphism is the virtual keyword. It is powerful and allows components of the test environment to change from test to test without needing to recompile. Revisiting the requirements that were previously defined for incremental compilation and elaboration snapshots, the dynamic configuration of the UVM environment that was just presented enables the requirements to be met. Incremental compilation and elaboration snapshots and the compute time savings they offer are now a reality. Since incremental compilation and elaboration snapshots have been achieved, I'll now focus on how sequence override is used to achieve simulation snapshots. On the left, I depict the one-to-one UVM test to sequence relationship that my organization has historically used. Each test starts one main sequence, which would stimulate the DUT as specified for that test case. This approach of having each UVM test run off a dedicated sequence is acceptable and may be well suited to some projects. In this example, the two tests did not share a common stimulus, such as a common initialization sequence. Where simulation snapshots add value is in allowing a long initialization sequence to be simulated once and subsequent simulations to pick up where it ended and spend the compute time on new and interesting stimuli rather than on initializing the DUT again. In investigating simulation snapshots for my organization, the Cadence simulator was used. Its simulation snapshot method, called process-based save restart, requires a single UVM test from which different sequences can be started. The code on the right provides an example of this single UVM test. In this example, the test first starts an initialization sequence and then starts a stimulus sequence. The simulation snapshot is created between the two sequences. The first invocation of this test would create the simulation snapshot and run the default USB sequence-based sequence. Subsequent invocations would use the simulation snapshot and override USB sequence-based with a different sequence to achieve a new stimulus. Sequence override is achieved through inherited sequence classes. 3 sequences are declared on this slide. The first, USB sequence base, is a sequence that tests USB on the left starts by default. The other two sequences, sequence exercise DMA and sequence suspend resume, inherit from USB sequence base. Because of this inheritance, an invocation of test USB after the creation of the simulation snapshot can go straight to the point where initialization has already been completed and execute a new and interesting stimulus by overriding USB sequence base with the derived class. I previously reported that using elaboration snapshot saved 8.6 minutes per test in a benchmark of my organization's test bench. Simulation snapshots can save even more by removing duplicate simulation cycles from the overall regression. Across the 2,000 test regression, the savings can easily amount to days of processing time. I have now shown how using the dynamic configuration power of UVM can eliminate repetitive compile and elaborate time. I've also shown how the use of sequence inheritance and override can eliminate some simulation time. Next, I'll talk about institutionalizing the power of UVM. Given the efficiency gained by fully adopting the dynamic configuration power of UVM, it is important to enable that adoption. To that end, I recommend some steps. First, data that shows the efficiency that could be gained is a good motivator. In the case of my organization, the idea of saving 12 days of compute time per regression is quite appealing. Second, the creation of UVM test benches can be automated through the use of scripts and templates. This template-based automated test bench generation guarantees a similar look and feel across test benches and builds in the elements needed for dynamic configuration from the start. Finally, a documented methodology, periodic knowledge share, and a review of the test bench at the start of each new project will help to institutionalize the full adoption of UVM. I'm going to talk more about the methodology and the test bench itself. Sequence inheritance is critical to the use of simulation snapshots, at least with the Cadence simulator. Given its criticality, my organization formalized a plan for sequence inheritance. I previously showed USB sequence base and two sequences derived from it, sequence exercise DMA and sequence suspend resume. USB sequence base was used by default in the test case run that generated the simulation snapshot, and the other two sequences could override it during subsequent runs using that simulation snapshot. The way I envision using simulation snapshots across my organization is for each subsystem owner to create a simulation snapshot with the proper initialization for the subsystem. This implies a sequence class hierarchy where every subsystem has a sequence base class that derives from the DUTS sequence base class, as shown in the figure in the upper right. The intent is for DUT sequence base, defined on the left here, to serve as a sequence base class in a top-level test bench. It declares elements that might be common to all derived sequences, such as register models and tasks to reset the DUT. Then, when a suite of tests requires components, functions, and tasks that are unique to it and do not belong in DUT sequence base, a derived subsystem-based sequence class, like USB sequence base, could be used. This subsystem base class derives from DUT sequence base and declares elements specific to its suite of tests. Other test sequences for that subsystem, for example, sequence exercise DMA and sequence suspend resume, would then derive from the subsystem's base sequence class. In addition to creating a plan for sequence inheritance, my organization wrote a script and templates to automate the creation of UVM test benches, build in the elements needed for dynamic configuration, and lay the groundwork for the sequence inheritance needed for simulation snapshots. The script generates the test bench module, shown on the left. The test bench declares a virtual interface for each agent and instantiates the DUT. You can see in the initial block that it puts the system Verilog interface for each agent into the UVM config DB and then calls run test. Run test faces all the components, starting with the UVM test through building, connecting, running, and more. Follow along now through the diagram on the right-hand side. The UVM aspect of the test bench is built starting with the specified UVM test. The UVM test is derived from the test base class, which we generate using our scripts and templates. The test base class's members include environment and agent configuration objects, the UVM environment itself, and possibly other components like a UVM register model. As shown before, a test may choose to override a default configuration, a default environment or agent configuration through an overriding function. Let's take a closer look again at the UVM test base class. During its build phase, the test creates and configures the environment configuration object. Then for each agent, it 1. Creates the agent configuration object, then gets the appropriate virtual interface out of the UVM config DB, assigns that virtual interface to its agent configuration objects, and then further configures the agent. The test then creates the environment. And in its connect phase, the test connects sequencers from the active agents in the environment to sequencers in the environment configuration object. All of this is to show that the test does a lot of manipulation of the configuration objects. After the test build and connect phases are done, manipulating the configuration objects, sequences are run during the run phase. This code snippet shows how the sequences use the environment configuration object in order to access various sequencer handles. The sequence base classes get the environment configuration object from the UVM config DB in order to use the sequencers that were connected by the test. The UVM environment also gets the environment configuration from the UVM config DB and uses it to determine what agents, scoreboards, and coverage classes to create and connect. These examples demonstrate the importance of configuration objects in the overall structure of a UVM-based test bench, as well as to its dynamic configuration. The UVM test uses these configuration objects to configure and convey information to the UVM sequences and UVM environment and beyond. In summary, while macros do have value in a test bench, they should not be used to configure the UVM environment. Instead, use UVM to dynamically configure a test environment. For this, the virtual keyword and the passing of configuration objects between the test, environment, and sequences are key to the dynamic configuration, as is the ability to override sequences and other class types. Taking full advantage of these methods enables the use of elaboration and simulation snapshots for more efficient simulations. Beyond what I've discussed today, there are still more powers to be gained. Realizing these powers takes an investment in knowledge, methodology, and infrastructure, but there are rewards to be reaped. Thank you for your time.